Okay, Math 352, welcome back again. We're up to lecture 14, and today we're going to continue on our optimization sort of applications of this course. And we're going to look at a more theoretical area that does have many applications, but this lecture is going to be kind of more theoretical. And we're looking at the concept of duality. Now, duality is, well, and one way of thinking of duality is when you've got an optimization problem, we can construct another optimization problem called the dual that is related to our original problem and can actually be really useful in solving the original one. Okay, so some of you who've done, for example, economics will have come across some of the concepts in this lecture, but they may not have been presented to you in quite the same way as you're going to get them here. So I'm going to start off with some definitions that are sort of in the context of more general optimization problems, and then we'll start looking at how we can apply this to linear programming, because the main optimization we're going to be doing in this course is linear programming. So that's what we'll look at. Okay, so let's get started. So we're looking at what is called Lagrange duality, or as far as we're concerned, just duality. And I'm going to start off with a definition. So consider a general optimization problem. So we looked at this one briefly just at the start of linear programming. So a general optimization problem in standard form. What does this look like? Well, if you remember from way back when, it basically looks like this. Minimize over x some objective function. Okay, for our linear programs, it's just C transpose x, subject to a number of constraints. There are inequality constraints, which conventionally you write as less than or equal to, and let's have m of those, and some equality constraints, and we'll have p of those ones. Okay, with x in Rn. Okay, so we define the Lagrangian is defined as follows. Now I'm just going to give you the definition and I'll explain it afterwards. So L of x, lambda, and nu, okay, that's nu, not v, the Greek letter, is equal to f naught of x plus the sum I equals 1 to m of lambda I fi of x plus the sum I equals 1 to p of nu of I hi of x. Okay, so that's our definition of a Lagrangian. Now one thing to note, just briefly, some authors, so if you get any book on optimization out, some authors use minus instead of plus here. Okay, the problem's the same, but the convention is different. We're going to use plus because I just think it works a bit nicer, and it seems to be more standard these days. Okay, so the scalars lambda I and nu I are called Lagrange multipliers. And yes, these are the same type of Lagrange multipliers that you've come across in second year calculus. Okay, just it's kind of in a more general setting here. And we call the vectors of Lagrange multipliers, lambda and nu, dual variables. Now we can actually do something else with our Lagrangian. The next thing I'm going to define, I'm sorry, it's going to be definitions for a few minutes here, is what we call the Lagrange dual function. Okay, so it's related to the Lagrangian, and it's defined as follows. G of lambda and nu, so it's a function of the dual variables only, is defined to be the infimum over x. Oh, by the way, D is the domain, Okay, it's basically the domain of this entire problem, is the intersection of all the individual domains, and is unempty. Non-empty. It's a better choice of words than unempty. Can't go making up words on you guys, that would be no good. Okay, so the Lagrangian is the infimum over all x of the Lagrangian. Okay, so it gets rid of the x by taking the minimum or the infimum over x. Okay, so we could write that out in full as well as the infimum over x of f naught of x plus the sum of lambda I fi of x plus the sum of nu I hi of x. Okay, a couple of notes we should make about this. If we're minimizing this thing over x, it's entirely possible that we could make our Lagrange dual function arbitrarily small. Okay, or arbitrarily negative, should I say. So, if the Lagrangian is unbounded below, we say that the dual function takes on a value of negative infinity. Okay, it's slightly abusing notation there, but the concept's pretty clear. Okay, so the dual function takes on a value of negative infinity. Okay, now what can we do with this Lagrange dual function that's actually useful? Okay, I'll tell you. So let's just get to the next page. Well, it turns out that our Lagrange dual actually gives us a lower bound on the optimum of the original optimization problem. Okay, so if lambda is greater than or equal to 0, okay, so for all the lambda dual variables, not the new ones, just the lambda ones, then g of lambda nu is less than or equal to p star, where p star equals f naught of x star is the optimal value of the original problem. Okay, so how do we justify that? So I'm saying that if we choose a vector of lambdas greater than or equal to 0 and any vector of nu's, then plugging that into our dual function gives us a lower bound on the optimum of our original problem. Okay, so proof. Suppose x tilde is a feasible point for our original problem. In fact, I'll give that original problem a name or a number. So let's just call this equation equation 1, since I'm going to keep referring to it. Let me make it blue. How about that? There we go. One blue, equation 1. Okay, so suppose x tilde is a feasible point for our original problem, i.e. fi of x tilde is less than or equal to 0, and hi of x tilde equals 0. And also suppose that lambda is greater than or equal to 0. And then, if we plug this into our Lagrangian, L of x tilde, lambda and v, equals f naught of x tilde plus the sum of lambda I fi of x tilde plus the sum, let's just move this across a little, of nu I hi of x tilde, which, well, let's have a look at what that does. Okay, well, if our points are feasible, then all the hi of x's are going to be equal to 0. So these ones will go away. These terms here, well, the lambdas are positive, the fi's are non-positive, so each one of these terms is less than or equal to 0. So our Lagrangian of our feasible point, lambda and nu, is less than or equal to f naught of x tilde. Okay, so we can follow that up by saying it follows that for any feasible point, and lambda greater than or equal to 0, that g of lambda and nu equals the infimum of lambda of x, so L of x lambda and nu. Well, that's got to be less than or equal to this one here, because that's just a particular value of x. Our infimum might be lower than that, so we can plug that in, which in turn is less than or equal to f naught of x tilde. And what else can we say? If we just choose x tilde equals x star, then g of lambda and nu is less than or equal to p star equals f naught of x star. Okay, and that's all we needed. So basically our dual, one useful property of it is if we plug in some lambdas and nus, then we get a value which is a lower bound on our objective. Okay, well there's a very natural next step to ask. If our Lagrange dual gives lower bounds on our objective, what is the best lower bound we can get? What's the greatest one? So this here, the problem of finding this greatest upper bound is known as the Lagrange dual problem, or just the dual problem. Okay, let me just for a second confirm this is still recording properly. Yes. Okay, so the Lagrange dual problem, what is the greatest upper bound, sorry, greatest lower bound on P star we can get? Well, this problem of finding this is known as the Lagrange dual problem. So it's a maximization problem now over the dual variables g of lambda nu subject to, don't forget it's only a lower bound, only gives a lower bound if our lambdas are positive. So what we have here is just another optimization problem. Okay, it's got some different variable names, but it's just another optimization problem, the same kind of form as we've had before. Okay, this is the Lagrange dual problem. Okay, we say that lambda and nu are dual feasible if lambda is greater than or equal to 0, and our objective is not negative infinity. And finally, we refer to lambda star and nu star as dual optimal. If they are optimal, with this equation here. Okay, and just to match my notes, I'm going to call this equation 5, even though we haven't had 2, 3, and 4 yet. Okay, so that's our definition of the dual problem. So you can think of the dual problem as, one way to think of the dual problem is to try and find the greatest lower bound we can get on our original problem. Now it turns out for quite a few important classes of optimization problems, the upper bound, the greatest lower bound you can find here is actually p star. It's actually the value of the optimal objective for the original problem. So in a sense, for a number of problems, including linear programming, solving the dual gives you the optimal value for the original problem as well. So we're going to sort of take a step back from this theory now, and we're going to start applying it to linear programming. So that's sort of the background, and it's not really what this course is about too much, so I just thought I'd give you the very short version. So how does duality work when we apply it to linear programming? Okay, so to start with, we'll just derive the dual problems of a couple of standard linear programming forms. Okay, so, oops, you apparently don't want to write anymore. There we go, we're awake, that's good. Okay, so, first one we'll do. Let me get my act together. Right, gremlins are gone. Okay, the first one we want to do, example 1. Standard form LP. Okay, well that's the type of linear program we've been dealing with all the time, and we know that we can write any linear programming problem in this way. So we'll look at this one first. So it's minimize over x c transpose x subject to ax equals b, and x is greater than or equal to 0. Okay, so basically we'll just go and apply our various definitions and see what we can come up with. So the Lagrangian so we need the Lagrangian first. L of x lambda in nu equals f naught of x, that's C transpose x. What next? We need to multiply, if we just look back to the definition for a second. I'll do the equality ones first. Every equality constraint equals 0 has to be multiplied by an element of nu. So the way we do this, for our sort of matrix form, is like this. Nu transpose has to be the equals 0 form, so ax minus b. Okay, if you expand that out, you basically get one element of nu multiplies one equation, ax equals b. And don't forget we've got some, we have inequality constraints as well, and the inequality constraints are for the form fi of x is less than or equal to 0, so we get a minus lambda transpose x. Okay, so that's just multiplying each of our non-negativity constraints by a lambda and making it negative because they need to be less than or equal to form. And we're multiplying each of our equality constraints by a nu, and we're adding on our objective. Okay, it's more useful to write this thing with all the x terms put together. So the parts of this that don't involve an x, there's just a nu transpose b, and we tend to write it like this. It's the same number, whether you take the transpose of that expression or not, it's just a number, plus A transpose nu minus lambda plus C transpose X. Okay, it's just the same expression. I've taken, if you expand probably the easiest way to see that this is correct is to take this expression here, expand it out, and verify that it's the same as this one up here. Okay, if it's not immediately obvious to you why this works, just take this one here, expand it out, and you should be able to match up the terms with this equation up here and see why I've done what I've done. Okay, so that's the Lagrangian. There's a term involving the dual variables only, and a term that involves x. Okay, so the next thing we need is our dual function. What do we have? Well, g of lambda and nu equals negative b transpose nu plus the infimum over x of a transpose nu minus lambda plus c transpose x. Okay, what's this thing equal to? Well, that's kind of interesting. If we look at this term here, think about it for a second. You might want to pause it so you don't get the answer straight away. What happens here? If we're minimizing or finding the lower bound on this term here, the A transpose nu minus lambda plus C transpose X, what happens if this term here is non-negative, or sorry, is non-zero? If there are some numbers in here, okay, so it's not zero, then what happens is, pause now if you want to work it out for yourself, otherwise, what happens is, you can choose a value of x that makes this thing go to negative infinity. For example, if one of the components of this vector was, say, 1, then you could choose the corresponding value, the corresponding component of x to be arbitrarily negative, and you get negative infinity. Likewise, if one of the components of this thing was negative 1, then you could choose the corresponding x component to be arbitrarily positive, and your dual function will still be negative infinity. So the only way that this function here can have a value that's not negative infinity is if this vector is equal to 0. Okay, so this vector here that I've underlined in red must be equal to 0. So basically we've got two cases here. It's either going to be equal to negative b transpose nu if A transpose nu minus lambda plus c equals 0. Otherwise, we can choose an x that makes it negative infinity. Okay? So remember that our dual problem, okay, which is what we're going to do next, is to find the maximum value of g. And notice that g is negative infinity if this term here is not true. So we're only going to consider values of lambda and nu that satisfy this constraint. Otherwise, it's infeasible. So is maximize over lambda and nu negative b transpose nu subject to A transpose nu minus lambda plus c equals 0, and lambda is greater than or equal to 0. Okay, and we can actually write this in a different way as well. Note that this one here can also be written as negative A transpose nu plus lambda equals, let's see, that'll be C. So think about that for a second. What does this look like? We've got something plus a vector of positive variables equals the right hand side. These actually look like the lambda as slack variables for some inequality constraints. So we often write this particular one, or equivalently, we have maximize over nu of negative b transpose nu subject to, so we can just take the slack variables out and write these down as inequality constraints. Negative a transpose nu is less than or equal to c. Okay, so these are kind of two ways we can write the dual problem for a standard form LP. And depending on how you're solving it or what you want to do with it, one or other of those forms may be more useful to you. Okay, so that's kind of interesting. We've taken the dual of a linear program And what we've got is another linear program. So our standard form LP has turned itself into an inequality form LP in the dual variables. We could also write this as minimize over nu, or B transpose nu if we wanted to. Okay. So what are the differences? Well, instead of our constraint matrix being A, it's now A transpose. So it's a different shape. And basically the roles of C and B have been interchanged. Now C is the right hand side of the inequalities, and B, which was the right hand side before, now appears in the cost. Okay, so that's one example. We're going to do another one. So we've just done standard form linear programs. Now we're going to do inequality ones. Inequality form LP. Okay, so this one looks like this. Minimize over x, C transpose x, subject to AX less than or equal to B. Okay, so no equality constraints. So we only need lambda. Dual variables. We don't need the new ones. Okay, so let's just run through the steps. So first we need the Lagrangian. It's just going to be L of x and lambda this time because we don't have any equality constraints. So that will be C transpose x plus lambda transpose AX minus B. Remember, the thing that we're multiplying the lambda by is a constraint of the form fi of x less than or equal to 0. So AX minus B satisfies this form, and this just expresses that we're multiplying each one by a component of lambda. And once again, it's helpful to rearrange this so that we've got the lambda components and the x components separated. So we can have a minus B transpose lambda plus, and again I encourage you to just verify for yourself that this expression here is correct, A transpose lambda plus C times x. Okay, so there's going to be an A transpose lambda here, all transpose, sorry, times x. That A transpose lambda term comes from in here, and the C transpose x term comes from just here. So the dual is just going to be g of lambda now. And once again, we've got the same problem. If this vector here is non-zero, then it's going to be unbounded below. So it's going to be negative infinity. And if this vector is 0, then it's going to be negative B transpose lambda. Otherwise. So the dual problem is to maximize this. So I want to maximize negative B transpose lambda subject to feasibility. Okay, we can't have a negative infinity objective, so it must be subject to A transpose lambda equals negative C. And don't forget the one that we don't always write down, lambda greater than or equal to 0. Okay, that's also very interesting. What does this problem look like? Well, this just looks like standard form linear program. If we wrote it as a minimization problem of B transpose lambda instead of a maximization problem, then this is a standard form LP. Okay, so the dual problem of an inequality form linear program is a standard form linear program. And like we saw just before, the dual problem of an inequality of a standard form LP is an inequality form one. So this is kind of, well, duality is the word I'd use, except that I'm already using it. There's an interesting relationship here whereby we get inequality constraints and equality constraints basically swapping roles. and we get therefore inequality form and standard form LPs as being joules to each other. Okay, so let's continue on. A couple of things to note here. In both of these examples, the number of primal I used a word that I haven't defined. The number of primal constraints equals the number of dual variables. I'll define primal in a second. And vice versa. Okay, this is basically because in both of these problems, the constraint matrix A becomes A transpose. So for this problem here, we have M constraints and N variables. This problem here, we have M variables and N constraints. Okay, so we're interchanging the number of constraints and variables, which can be quite useful when we're trying to solve the dual. And I'll talk about that a bit later. Okay, now by the way, the primal refers to the original problem. So whenever I talk about the primal, I'm just talking about the original optimization problem that we started with. Okay, it's easier than saying the original problem all the time. So the word we use is primal, and dual refers to the dual problem. So I'll often talk about the primal or the dual, and that's what I mean. Okay. So let's just have a look at a few properties of the dual here. So what we're really interested in is just getting our head around the different types of behavior we might expect from these problems. So we'll call this solution scenarios, because that sounds kind of cool. Okay, so just note that for any, so what we did before, any primal feasible x, so you'll start to get the hang of how I'm using the word primal, and dual variable lambda and nu, sorry, dual feasible, we have well, like we were saying before, vice versa, g of lambda and nu is less than or equal to f naught of x. Okay, well we know that g is a lower bound on f naught of x star, so it's definitely a lower bound on f naught of x. Okay, I'm just going to fix that in my notes because I had it back to front. Okay, so we've got 4 different scenarios that can come up here, and let's have a look at them one by one. So the first one, if the primal is unbounded, okay, we know that sometimes we get optimization problems where the problem is actually unbounded. That means we can make f naught of x arbitrarily small or arbitrarily negative. And this inequality here forces g of lambda and nu to be negative infinity. So this implies that g of lambda nu equals negative infinity, and hence the dual is infeasible. Okay, so that's interesting. If we've got an unbounded primal, then we can make our f naught as small as we like, or as negative as we like, and that forces the dual to be infeasible. Okay, we can say the opposite as well. If the dual is unbounded, then g of lambda and nu can be made arbitrarily high, made arbitrarily positive. Okay, which implies that the objective for our primal is infinite, which is another way of saying the primal is infeasible. Okay, so once again I've used infinity in a slightly loose way again here, but it's actually not. Often in the literature, what you'll do is you'll say, instead of setting up let's say you've got a constraint x is less than 0. One way you can implement this, x is less than or equal to 0, is you can say that, so we say if I of x, if I of x is less than or equal to 0, one way of implementing this is to say that if tilde I of x, or if bar I of x is equal to if I of x, if x is less than or equal to 0, and positive infinity otherwise. Okay, so often when you're programming, if you want to implement a constraint like this, sometimes you might come up with something like this. Okay, you might, because you can just set things equal to infinity if you're using a computer. So the sense I'm using infinity is just to kind of express an arbitrarily high number, which actually stands for the problem being infeasible. Okay, so that's two of our scenarios. Number 3, the primal and dual may both be infeasible. Okay, and what does this look like? Well, if we've got the problem, let me just check something. Maximization, so the primal, so I'm not trusting my computer to behave itself today, that's why I keep flicking up there like that. Let's say the primal is minimize over x, negative x2, subject to the following couple of constraints, x1 less than or equal to 1, negative x2 less than or equal to 1, and x1 and x2 greater than or equal to 0. Now you can check for yourself that the dual problem, useful exercise if you want to pause and you've got a bit of time, is maximize lambda 1 minus lambda 2, subject to lambda 1 minus lambda 3 equals 0, negative lambda 2 minus lambda 4 equals 1, and lambda 1 through to lambda 4 greater than or equal to 0. Okay, firstly note that the primal is infeasible. We can't find, have I written this correctly? Yes, this one here says that x2 is, I've made a little mistake here, there should be negative 1 on here. Okay, x1 is less than or equal to negative 1, and x1 is greater than or equal to 0. So our primal is unbounded, is infeasible. We can't find an x1 that satisfies both of those constraints. And likewise our dual, you can drive that for yourself. We can't have negative lambda 2 minus lambda 4 equals 1 with lambda 1 through to lambda 4 being non-negative. That's not possible. Okay, so in this situation we've got a primal and the dual, both of which are infeasible. So note the thing I wrote down wrong, there's supposed to be a negative sign there on the 1. Okay, so finally, so that's solution. That's scenario number 3. The final one is the one that we normally have. Finally and typically, both the primal and dual have solutions. Okay, so those are the 4 different types of behavior we can get. We can get if either the primal or the dual is unbounded, it implies that the other one is infeasible. We can have both of them infeasible, and normally, which is what we want to happen, both of them have solutions. So the last thing I want to talk about in this lecture is the relationship between the solution of the primal and the solution of the dual for linear programs. Okay, so I'll call this optimality. So what I'm going to do is I'm going to consider a primal in standard form. So we're just using a regular standard form LP. And let's say we've solved it already and we've got the optimal basis B. Okay, so we therefore have xb equals AB inverse B, just like we've been doing. Xn equals 0, and the optimal cost, C transpose X star, equals CB transpose XB equals CB transpose A B inverse B. Okay, without loss of generality, that's what WLOG stands for, we can assume that the optimal basis is the last m columns of A. That A equals AN AB and X equals XN XB. Okay, we can just, if that's not the case, we can just rearrange the variable order so that is true. Okay, so this is an LP in standard form. So the dual is maximize negative B transpose nu subject to the following set of constraints. Negative A transpose nu is less than or equal to C, like we did before, which gives us negative A N transpose, negative A B transpose nu less than or equal to CB and CN. Cool. Okay. So now I'm going to give you a magic number. So consider nu equals minus CB transpose AB inverse. Okay, why am I doing this? Well, i.e. nu transpose equals negative AB inverse transpose CB. Okay, let's just write the transpose the right way around. Sorry, so it's nu transpose equals that, or nu equals that. If we plug this here into our objective, the reason I've chosen this is that if I stick this into my objective here, I'm going to get the same value of my optimal cost. Okay, so C transpose X star, well, this is so negative B transpose nu equals negative B transpose A negative AB inverse transpose CB. Okay, take the transpose of the whole thing because it makes it a bit clearer. CB transpose AB inverse B, which equals C transpose X star. Okay, primal and dual objectives. Objectives are equal. At this point in time, that's not saying a whole lot. It just means we've chosen a value of nu that forces the primal and the dual to have the same objective. Now, if that nu happened to be feasible, then this would be the optimal solution to our dual. Okay, we know that the dual can't have a higher objective than the primal objective, so if nu is feasible as well as having the same value here, we know that we've solved it. Okay, so if nu is also dual feasible, then it must solve the dual. Okay, so we'll check constraints. So we'll be brave and bold and plug in our slightly nasty looking expression in. So what have we got? We've got negative AN transpose AB transpose times nu AB inverse transpose CB is less than or equal, at least we hope so, CN CB. Okay, so what we want to do is see if this is actually true or not. Okay, so I'll expand this out, the two sets of equations corresponding to the first, n minus m rows and the final m rows. So from the top set, we get Cn. I'm just going to move it all to the right hand side. Cn, I'm going to have two negative signs here, and I'm going to shift it across so that will leave me with a negative sign. Minus AN transpose AB inverse transpose CB is greater than 0. And the bottom set says AB transpose AB inverse transpose CB is less than or equal to CB. So these are the top rows and bottom rows. Okay, this one here just becomes CB less than or equal to CB. Okay, AB transpose times AB inverse transpose is just the identity. Okay, so is this true or not? If it is, then we've solved our dual. So how do we know? Well, this one is fine. Okay, obviously CB is less than or equal to CB, that's trivial. This one here, not so obvious, except that we've actually seen that term before. That there, what is it? Maybe think about that for a moment before I give the answer, which I'm about to give you now. That term there is just the vector R of reduced costs. Okay, so we didn't really expect to find them cropping up here, but that there is our vector R of reduced costs. At optimality, which is where we are at in the primal, R is greater than or equal to 0. That's our test for optimality. Okay, so this means that both sets of constraints are satisfied, so we'll give that one a tick as well. Constraints are satisfied. Therefore, we are dual optimal. Okay, so the important takeaway point here, primal and dual have the same optimum. Okay, and one really simple-minded application of that is, if you don't know if you got the right answer or not, you can solve the dual as well. And if your dual gives you the same solution, then you're going to be pretty sure that your answer is right. Okay, so really important point to remember here. When we're dealing with LPs, the primal and the dual have the same optimum. They are one of a class of optimization problems that have this property, and that is really important in practice because a lot of algorithms for solving linear programs, other than the simplex method, actually solve the primal and the dual at the same time. And what they try and do is they try and reduce the gap between the optimums of the dual and the primal. Okay, so they look at the objective values of the dual and the primal, and once that gets down to 0, that's another way of seeing that you've solved the problem. Okay, so remember this, the primal and the dual have the same optimum objective, I should probably say. Okay, that's probably about the end of this lecture, I think. I don't think there's anything really more I need to say. I'll be seeing all of you tonight at your test, so I hope your studying is going well, although I guess once you're watching this lecture you've been through that already. So I'll see you all again when I see you, and until then, have a good weekend.